morning, everyone. Thank you very much for inviting me to speak here to you today. Burnell mentioned I will be talking about some of the reservoir modelling we've done on the geothermal field. The outline of my talk will be to look at the purpose of the modelling project, a little bit of a summary of the conceptual model that's relevant to the numerical reservoir model, a discussion of the structure of the numerical reservoir model, verification of that model, then what predictions were for the expansion scenario that has been considered for the reservoir, and then finally looking through a model of the surface features that we developed to predict what might happen to those in the future. So the purpose of this work was to develop a numerical reservoir model of the geothermal field with a consenting process that Burnell mentioned. In New Zealand, before you can undertake a new development, you need to obtain what is called a resource consent. This gives you permission to extract fluid and produce electricity. And in order to obtain such a consent, you need to indicate what the impact of your development will be on the environment. The specific objectives for this project were firstly to obtain an acceptable match to the historical data measured in the reservoir. An important component was to use a dual porosity model to accurately model injection returns. Then to consider the effects of the expansion on the reservoir and the environment, and make predictions on the impact on surface features. So I just want to look briefly at the conceptual model. You've actually already seen this, so I won't mention this in particular. The relevant points are that we do have a low permeability capping structure to the reservoir, and then within the permeable part of the reservoir, most of that permeability is due to fractures and faults. You've seen this out before as well. I just want to highlight that for the current operation, this is the area where the production and injection wells are. The production wells are sited around here, and the injection wells are here. The thermal features that are most significant are in this part here. And one of the conditions of the current operation of the reservoir is that pressures must be maintained in a well that's sited just alongside these thermal features. That well is known as NG13. So we have the geology which we've discussed. So these are the characteristics of the reservoir. The temperatures within the permeable part of the reservoir, where we know we have good flow, are approximately 230 degrees, but we do see hotter temperatures in the basement, as was shown before. Temperatures have been measured up to 300 degrees, but those measurements have been taken. Where those measurements have been taken is believed they're wrong. It's very low permeability. There was testing undertaken in the 1980s before production started, and that testing suggested that there was a highly fractured reservoir with very good permeability. And as has been mentioned by Burnell, there are some significant non-condensable gases in the reservoir with CO2 concentrations, perhaps about 1.5%. Seen this already, so I don't think we really need to add anything to this. We're postulating that the upflow into the, so I will sort of mention the permeable part of the reservoir, and by that I mean this region between perhaps minus 1,000 metres below sea level and the bottom of the cap, which is about minus 500 metres above sea level. So this is sort of where we see permeability within the reservoir. Where we believe hot fluid comes up into that shallow portion of the reservoir is in the northern part of the reservoir near the well NG5. We do have a number of data sets that have been collected both during testing before production started and since production has been undertaken within the reservoir. There are pre-production pressures and temperatures. So you've seen this before. So we have this conductive profile through the cap. We have another conductive profile through what we believe to be a low permeability part of the basement. And then within the permeable part of the reservoir, we have a relatively uniform temperature of about 230 degrees. There have been measured changes to the reservoir pressures. You can see here two plots. So the first plot shows us downhole pressure measurements. The upper curves that we see here are from the production wells, and the lower curves are from the injection wells. And so around the production area, we've had a pressure drawdown. We've got time along the horizontal axis, and we have pressure change on the vertical axis, and these are in bars. So the pressure change around the production wells is about 1.5 bar, which is a very small pressure change. It's much smaller than we've observed in any other field in New Zealand. Usually the pressure changes are more like 10 bar, or higher. The unusual feature of the pressure changes that we see is that we have large pressure changes around the injection wells. Typically, you would anticipate you'd have pressure increases around the injection wells and pressure lows around the production wells. Ngawha is a little bit different, and I think one of the contributing factors to this is that the use of full re-injection at Ngawha means that, and very low pressure decline, means that thermal effects play a significant role. So now we're injecting colder fluid into the part of the reservoir. As that fluid is colder, it's denser, so it occupies a smaller volume, and that means that the fluid in the rest of the reservoir needs to expand to fill that volume, which slightly lowers the pressure. This is an effect that I think we have in all our production producing reservoirs, but because the pressure changes are much higher in most reservoirs, you don't tend to notice that thermal effect, but it is important here in Ngawha. The bottom plot just shows continuous monitoring that's been undertaken in that well in G13 that I mentioned. It's consistent with the downhole profiles that we see. So from about 2001, we've had about half a bar of drawdown, which is from here to here, so that's about that half bar. So this is the continuous monitoring. This well has a condition on it that the pressures are not allowed to drop below, they're not allowed to fall more than 1 bar below the pressure in 2008. So they can't drop below 8 bars within the reservoir. We also have changes in production enthalpy as part of our data set. There's changes in the CO2 concentration that one showed, and we have some data from pressure interference tests that were undertaken in the early 1980s. And then in 2011, a tracer test was conducted, and this gives us some information about travel times in the reservoir. So, as I mentioned, the purpose of this work was to develop a dual porosity numerical reservoir model. A dual porosity model is a model that represents flows through fractures. So, typically in our geothermal field, we find they are fractures, and you can think of the flow paths as being high permeability, fast flow paths through fractures with a high storage but low permeability matrix around it. And the dual porosity model is a means to represent this process. It was developed within the oil and gas industry initially. It has been modified slightly for the geothermal context. In the geothermal context, most of the heat is stored within the matrix, within the rock. And what we find is that as we inject cold fluid into our reservoir, we cool the fracture quite quickly with slow movement of that cooling front into the matrix. So the fracture is actually cooled quite quickly, and this is in comparison to single porosity model, where you don't consider fracture flows, what you find there is that the thermal fronts, your cooling from injection fluid are much slower moving towards your production wells. So dual porosity models give you a better representation of the cooling effect from injection in the reservoir. The numerical reservoir model requires some sort of grid of elements. This is the one we use for NAPA. There's a liner grid across the, what we believe is the resource, delineated by the PC and the NT resistivity boundaries as well. So that grid, we apply certain properties of what we call, within the model, we call them different model rocks. So we have a very high permeability region, which sits across the production and injection wells, and as we move out from that, we move to something a little bit more moderate permeability, and then lower permeabilities outside of that, and then very low permeabilities on the outside. We've included a small upflow within the model, up in the northern section near that well NG5, where a little bit of calibration would put the rate of that as 10 kilograms a second. This is significantly smaller than what we typically see in the geothermal fields in the Taupo volcanic zone, which are more like 100 kilograms a second or higher. So we just want to look through the work on verifying the model, checking that the model is giving us a good match to the data. So to do this, we first run a natural state model. So we run the model for a long time before production is used. We compare the results of that model to measured pressures and temperatures. We then apply the historical production rates to the model and compare the changes to pressures, entalpies, and CO2 concentrations. We add the tracer injection to check against how the model performs with the tracer test, and we compare the model results to the early interference test that was done in the 1980s. So we're looking just quickly at some of the results. These are the matches to the natural state temperatures. They fit reasonably well. We're picking up the characteristics of the reservoir with the conductive profile through the cap, a conductive profile at depth, and then a relatively uniform profile throughout the permeable part of the reservoir. We even picked up a little bit of this inversion at the end here at the top as well. Some work still needs to be done. There's still some improvement that we need in some profiles. But overall, the match to the temperatures, particularly in the production part of the field, is good. This is the match to the natural state pressures. We're plotting here on the horizontal axis the model pressure in bar absolute, and on the vertical axis is the measured pressure. If the model matched perfectly, then all the data points would sit on this 45-degree line, y equals x. The dashed blue line is where there's a mismatch of 2 bar. So the model is a little bit high, but the 2 bar mismatch is quite acceptable for a numerical model. So overall, it's a good match to the measured pressure. These are the changes due to production now. So these are the changes in that monitor well, NG13 that I mentioned. As I said, we have a very small pressure drawdown at 1.5 bar, and the model has reproduced that very well. I'm particularly pleased with this level of match. Often matching pressure drawdown within 1 or 2 bar is considered a good match. Here it's much closer. We get a similar match to the pressures in one of the production wells in G4. Unfortunately, we're not matching that extra drawdown that we see in the injection wells quite so well. And I think the reason for this is that it is that thermal effect that I was mentioning of density, but I think that is a near well effect. It's something that occurs within 10 to 20 meters of the well, whereas the reservoir model, we have looked at model elements that are hundreds of meters. So I think we can't resolve the effects that are giving us this high level of pressure drawdown around the injection wells at the moment. These are production entalpies. This match is not as good as I'd like, but it's in the right ballpark. Matches to the other enthalpies are good. But there are some issues with that enthalpy. There are some issues with that enthalpy that I've showed there, just there. If we look at this enthalpy at early times, we find that it's inconsistent with the measured temperature in the well. So the measured temperature in that well, which suggests that we should be about 980 kilojoules per kilogram, is being measured at 900. This is an inconsistency that's been noticed in the reservoir. A lot of work has been done to understand it, but so far no explanation has been found for why the enthalpies do not appear to be consistent with the rest of the data we have about the reservoir. It's also inconsistent with what's been measured at the power station. So if we look again at what we see in NG9, we should be seeing some increase in enthalpy around 2008. That's not reflected in what happened in the power station. So no enthalpy increase was seen. So there are some issues with the measurement of enthalpies in this field. I believe that the TNT testing is probably accurate to about 100 kilojoules per kilogram. And if you add those uncertainty bars to the data, the model's doing as about as well as it can, I think. We also have changes in CO2 concentrations. So here we're looking with the red squares at the measured CO2 concentrations, and the blue curve is the model CO2 concentration. As Ronnie-san mentioned, this change in CO2 comes about because the injection fluid is being degassed. There's no gas in the injection fluid when it's put back into the reservoir. That degassed fluid then spreads throughout the reservoir and is finding its way back to the production wells. So this is giving us information about the long-term connection between the injection wells and the production wells, in particular the flow paths between those wells. We'll see similar good matches in the other two production wells, UG12 and UG4. We had a tracer test that was conducted in 2011. So a number of tracers are injected and put in some of the injection wells. Here we're going to look at the tracer that was put into the well EG16. The tracer test started in March 2011. And then we had about 4 months before we started to see returns in the production wells. The only well where we see the classic tracer return profile is in EG4. EG9 is quite a different profile than you would anticipate, and also EG12. I should point out that we are getting recycling of tracers, so you inject the slug of tracer into your well, that then goes back to your production wells, it comes back in the injected fluid again and is recycled. So you get recycling with the tracer, and this is this tail that we're seeing here is about 1 part per billion. It's the recycled tracer just going back through the injection fluid again. The model hasn't matched the tracer returns as well as I'd like, but we were constrained at the time how much time we had to develop this model. We're matching the arrival times, which is an important thing, and we're also matching the relative contributions of the tracer. So the less tracer is observed, the more we're explaining this tracer being seen in the production model. We've also matched the changes that we see from this interference test in October 1983. The red squares are the measured data, the measured pressure changes. We're looking at changes now of about 0.2 of a bar, so very small pressure changes. Again, the model is reproducing the time scale of changes. When a change occurs, it is seen back at the production, or it is seen back at the monitor well at about the right time. But again, the coarseness of the model, the fact that the model blocks are hundreds of meters in size, means that we're not quite able to match the extent of those changes. But for a production reservoir model, this is a good match for an interference test. So it's not just pressure changes, it's not just entropy, it's a number of different features, and it has a strong basis on the physical conceptual model of the reservoir. So we use this model to assess the impact of some proposed scenarios. There were two scenarios that are considered, one with a 25 megawatt expansion and the second with a 50 megawatt expansion. With the 50 megawatt expansion, it's undertaken in two stages, with a first stage of 25 megawatts in 2020, and the second stage up to 50 megawatts in 2023. In order to run this scenario, we needed to estimate the amount of injection that was going to occur. In the field, they are injecting all the fluid that they have available, but because they have this loss of gas, it means it's not 100%. And also there are some other losses that occur through operational aspects. There are spillages and things like that during the plant shutdown. So it's not quite 100% that's going back in. And we adjusted, we've kept this loss and spillage factor the same, but we adjusted the loss of gas to decrease with time from about 0.5% at the moment to a very low value at the end of the forecast. And then we continue to use supplemental injection to control the reservoir pressures required. And we're able to achieve the necessary control of the reservoir pressures. So here we're seeing the two scenarios, the 25 megawatt expansion in blue, and the 50 megawatt expansion in red. And we can see that we can maintain the pressure in this module well at the required level, which needs to be above about minus 2.5 bar. However, there are changes in other parts of the field. So at the module well near the springs, pressures are maintained, but further away from the springs where the injection, where these are new production wells that are quite distant from the injection wells, we're seeing some larger pressure changes. There are also some changes in enthalpy which will impact the power generation from the power station, and they'll need to be factored into the design of the power station. One of the wells, MP4, is actually showing quite a significant drop in enthalpy of more than 100 kilojoules per kilogram. That may require some changes to the plant. So overall, the modelling suggests that the proposed expansion can be undertaken with only a minimal impact on the reservoir. But as Ron mentioned, the surface features are very important, and the springs are highly valued by the local community, and we really needed to make some assessment of what the changes in the reservoir would mean for the changes in the springs. Unfortunately, this reservoir model that we've been working with is too coarse to really make those predictions around the springs. As I mentioned, the reservoir model has blocks that are hundreds of meters in size, which is required to get a model that is feasibly run. We need much finer detail to model the springs, so we've developed a separate model to do this. Essentially, we've just tried to model the flow through the cap rock of this system. So what we see at the springs is we've got fluid from within the reservoir coming up through some conduit in the cap rock. It then mixes with the surface waters, and as you saw from Robbie's slide, we get different spring characteristics depending on that level of mixing with the surface waters. Now, we decided not to try to model this process of mixing with the surface waters because this involves quantities or involves things that are not within the control of the project, such as the amount of rainfall, which would change the groundwater flows. So what we looked to do was to see what is the flow of geothermal water that is coming into this surface water. If we can demonstrate that that clearly changes, then that means that the geothermal project will only have a minor impact on the flows of the springs. So we constructed a model grid. So this model is about 1,000 meters in length, about 100 meters that way. We have very fine resolution around where the springs are. I think this grid block is about 1 meter in size. We're modelling, as I say, just the flow through the cap rock, which which is about 500 metres thick. We calibrate the model to measure temperatures. This is one of the wells that's sitting up at the edge of the model. So we made sure that we were matching the temperature profile in that well. We made sure that our pressures were consistent with the pressures that we observed within the reservoir. Then what we've done is we've fixed conditions at the bottom of the model, which represents the deep reservoir. We fixed conditions at the surface, which is the flow out of the reservoir, and then we've adjusted the permeability of that conduit to match what we believe the flows to the individual features. We've ended up with a model flow of about 1.3 kilograms per second. It's estimated that the flow to some of the springs is between 1 and 2 kilograms per second. After we've adjusted that permeability to match that flow and the pressures and temperatures, we then utilise the output from the expansion scenario to see what the impact on the spring will be. So we've taken the output from the expansion scenario from the reservoir model. We know how the pressures change in that expansion below the spring. We know how the temperatures change, and we know how the CO2 gas volumes change. So we progressively change those quantities within the reservoir conditions at the base of the model and look to see what that means flow through the conduit. Basically, it means there's almost no change in the flow to the surface. There's no change in the amount of steam in that flow, and there's no change in the temperature. But where we do see a change, we see a change in the CO2 content. So as we degas the reservoir, the fluid that will appear at the surface will also show reductions in gas content. So overall, the model is demonstrating that the impact on the springs will be minor, with the only impact possibly being a change in chemistry related to the change in gas. We did some work to understand what that could mean, and we ran a chemistry calculation using geochemist's workbench, where we took a reservoir fluid, we mixed it with groundwater to obtain a spring chemistry. We then reduced the CO2 content of that geothermal component to see what would happen. And we found that the main changes were then a change in pH, so we're getting slightly less acidic fluid, the pH changing from 6.2 to 6.95, and a reduction, as one might expect, in bicarbonate fluid. So those are the two main changes that have been seen, and this change in pH is relatively small in comparison to the natural variability of pH in that spring. So overall, we're of the view that the expansion that's been considered within the reservoir will have a negligible impact on the surface features. So overall, we believe we have a well-calibrated model for consenting purposes. We've matched many different aspects of flow within the reservoir. We've demonstrated that we can control the pressures in the reservoir through supplemental injection, and then we've undertaken a model of the springs which demonstrate the impact as minor. Thank you for your attention.